Okay, welcome back. This one's called Advanced 10 Volume Break 2 SC Impact Activation. This is where we're going to drop these objects onto a collision floor and use that collision impact position to drive the activation. Okay, to do this, we're going to go ahead and take our sources, take a look at our collision environment. We'll go ahead and initially position these guys up above. And we'll rotate them a little bit so they have a little more interesting collision impact point. Let's take this guy and scale him a little. Okay, so remember we've got our collision environment. We're going to need some gravity in here and a shape collision. Birth. This dynamic set needs to be named what it is inside of it. This is a volume activate example. Volume. But we're not going to be using this. We're going to turn that off right there. Remember, the volume activate operator itself is used to tell the actual volume break operator what position to use to cause the fragmenting, to activate the frags there. Okay, so we're going to also disable this volume cell. We don't really need that. This whole activate, let's remove. And you know what, let's actually also remove that guy. Don't need that. Okay, all cleaned up. Let's do this. Let's get a SC in here. Oops. SC is going to be dealing with the SC group because it's going to contain all of these. Our collision environment, we need this to be a neutron. And let's go ahead and set it to box mode, which is voxel grid 0. Edge samples 1 might be too low since this is a pretty, it's just one big face on here. We'll leave it at 1 and try that and see what happens. And our collision iterations contact, we'll leave that for now as well. We tend to leave these at the defaults unless they don't look right and need some adjusting to get proper sampling. Okay, so let's take a look and see. Where's our objects and is it volume breaking? So right now we've got this going on. Let's actually disable this. That's right, we need some gravity. Let's use a black box for dynamics, and we've got gravity. Let's sort all this mess out. Okay. And in this case, actually, remember our order of operations. What we're going to do is we're going to set up our VB here at the bottom. Okay, so, whoops, our gravity is affecting all particles. We only want to affect the VB system. Okay, that's a little high in space, takes a little too, actually, what's our force? Let's increase this to 200. Let's go ahead and move our sources a little bit closer to our floor as well. Okay. So we don't need these VB cells anymore. Let's take all that, remove. And then, let's see, boink. So we get a nice box falling, hitting the ground. Everything looks pretty kosher. Let's go ahead and grab this, delete that stuff, I don't need it. Okay, so here's what we do. Whenever there's an impact, we need to detect when there's an impact between our VB source and the collision environment. So to do that, we just need a couple in-group tests. First group, we're going to check and see, hey, are you in the collision environment? The other one's going to be, are you in the VB source group? Remember, collision particle A, collision particle B. These are based on the order in the group tree. So collision environment is way above VB source. So collision environment is going to come out of collision A. And collision particle B, of course, then will be the VB source whenever there's a collision going on between these two. So collision there, and we need to make sure both of those occur at the same time, or both of those are true when we evaluate. So we set up that and then what we're going to do is we are going to birth a bunch of our cell particles at the point of that impact. So do generator position born, grab our position into this collision position, and don't forget that you cannot mix the single star outputs and the double star outputs. They have to be used in the same kind of grouping. So all of these, from number down to collision B, those can all be used together with whatever wiring, or if you need also some separate wiring, you can use any of the single stars, but only the single stars can be together. You just can't mix them. Okay, so we're going to create some volume cells. Pistol shot, let's just do, say, 27, whatever for now. And let's go ahead and make their lifespan 1. Speed, speed is not so important. I'll actually set that at 0. Our variation 180, and our emission distance is going to be the big thing. So let's go ahead and watch what happens when that does hit and collide. Okay. Let's make sure our VB cells are being displayed as dots. Yes. Okay, so we need to actually control when this particular rule turns on. And so we'll connect that to the AND. So both of these particle groups must be involved in the collision in order to create VB cell particles at that position. Let's just make sure that. Okay. Bing. So now we see our green particles being created there. We're going to need a little bit more emission distance, and let's vary that up. Let's actually get more particles in here too. Pow. Okay. So now we get a nice kind of radial dispersion pattern. We can actually set this up, as we'll see in one of the iterator videos, how you can actually create directional patterns to point towards or away from things. But for now, this standard kind of emission distance spherical distribution will be fine. And what we're going to do then is, we've got these VB cells being created. We need to actually tell the volume breaker to use these VB cells to activate. Okay, so go ahead and turn this on. Now what's going to happen is our face, actually let's turn off our sources. The faces for the volume breaker on this particle have been allocated already. So we see those cuts appear. But you can, I wish Max would let me zoom around stuff in screen space there. So we can see all the outside edges, none of the inside edges. Those get created when the thing gets activated. Okay, now here's where we tell VolumeBreak to use the volume cells, the VB cells, to activate. Here on the VolumeBreak operator, we've got a bunch of different conditions that can be used to activate the cells. You can either use a light threshold, so if you want to pick some scene lights, you can do that. If you want to use a map, so whatever, something growing on the outside of this object map with whatever UV space. And then what we've got here is a helper. You can either use a scene object as a helper, or you can use a particle group as a helper. And so we're going to use the VB cells. And threshold distance here, again, is in world units. So it says whenever a cell is, X number of units away from one of these helper particles, then this cell is going to activate. So we're going to start this off kind of low because we don't want it to be too big. Remember, 10 units in this world space is, or in this scene scale, what are we looking at? Yeah, that's about 10 units right there. So let's go ahead then and let's trim it down to 5 for now. See what happens. Okay, so here we're about to collide. Pow. Okay, so it hits, and actually this is interesting. What happens is we only get activation kind of in this ring around where these particles are. So because these VB cell particles are being dispersed around here, what happens is these VB cells in the particle get activated, but they're kind of being dispersed in a spherical pattern, and so you get some of these VB cells too close to the surface still, and they're not anywhere near the part that gets activated. So one of the things we can do there is just increase the variation in our emission. Let's actually also double the number of our activation, number of VB cells being created. Pop. Okay. It's a little hard to tell in shaded mode, but okay. So we can see that whole corner of those frags being kind of activated. It looks like we may want to go ahead and change our volume break threshold back to 10. Now here's something interesting. The VB cells, you remember, we were telling these to have a lifespan of 1. That will actually, because what happens is, because they're alive for 1 frame, they're going to live through the whole evaluation. They're created here, so they live through the rest of that tree time, and then they, as TP starts to evaluate the tree again, they're still alive through this next whole phase of evaluation. Because we have the VB source and the volume break actually below the SC, we can tell these guys to have a lifespan of 0, meaning you're going to be created during the evaluation of this tree, and then once the evaluation of this tree is done, you're dead. They're only alive during that one time sample. So they're created in one rule of the time sample, and then once we get to the end, they die off. Okay, but because volume break is actually below SC, we're able to go ahead and activate. Whereas if we set VB above, the order of evaluation is going to occur that, hey, my lifespan 0, I'm only going to be alive this one sample, but hey, I'm the last operator in the whole tree, so guess what? I'm born and then I'm going to die. So you saw them appear, but there's no activation. That's because volume breaker actually needs those particles. So you can see that it looks like it should activate, but what we're seeing here is we're seeing kind of the they were actually created, I believe, on frame 24. Let's check or actually no, I'm wrong, on frame 25. So yeah, we do see them being created here, but volume breaker needs those particles to exist. Bang, so just right there. Volume breaker, because it's waiting for them on the next time sample down this tree, and their lifespan is 0, they die right here. Tree starts to evaluate again. Volume breaker says, hey, okay, I'm ready for those for my helper particles, but they're not there. They're dead already. Let's somehow rename those. Let's get that back in there. This would be a good time to save. Okay, so if we do want zero lifespan for our particles, and to have them activate the volume breaker. We need that volume breaker to be lower in the tree so that rule gets evaluated after they're already created. So the VB cells are created, zero lifespan. Next rule down, still in the same time sample, volume breaker says, hey, okay, are there any VB cells for me to use? And of course there are, and they're still alive in that time sample, so it can go ahead and activate and see those created. Throw in a little scale on those particles to make them shrink. Maybe they will loosen up a little bit and fall apart. But it doesn't look like they're going to actually come off of there just yet. Let's go ahead and help them out of there. Let's do this. Let's say at birth, give you a little velocity in any direction, and also throw in a little spin, just kind of try to twist them and get them out of there. Let's get our TP icon out of the way. It's conveniently right in the spot. So now we see them spread out there like that. Boom. Okay, let's watch what happens as this thing continues to hit. Now, sure, that's cool. It followed the rule. It did exactly what we told it to do. It said, hey, there was a collision between collision particle A and B. We don't really want all those displayed. There's a collision between these two particles. Go ahead and create these VB cells. Unfortunately, though, it doesn't really look too realistic when it does that, because you've got not a lot of velocity on this object. So watch what happens as this part rolls down and actually hits the surface again. Boom. It's just going to kind of continue to fragment. That rule is found to be true, and so it fires off the position born. Okay, so the way we're going to control that and make it a little more realistic is to throw in a particle data, and we're actually going to look at the speed of either particle. Not the position, but the velocity. Remember, velocity contains both direction and speed. What we can do is test with a threshold the velocity. And because this is a velocity being fed into a scalar value, it's going to go ahead and automatically derive and extract the speed value, which is the scalar component. Okay. So what we want to know is, hey, if either velocity is above, say, what's a good way for us to find this? Let's actually do this. Let's say get my, which one, VB source, get my particle data, and feed that into a memory operator just so I can read it and kind of see what the values are. Set that up so that it turns valid, and then we'll go ahead and turn on debug mode so we can actually see the kind of speed values we're getting for our VB source. So it starts off kind of slow. The force works its way until it reaches above 200, above 300, yep. So 300 pow, and then by the time it's rolling down here, the speed is right around in the 60 level. So we could do pretty well if we said, I want your speed at impact to be, say 100 or greater. So we don't need that. That was just for debugging. Let's go ahead and get a float in here because we're going to actually control both of these thresholds at the same time. We don't want to have to, come in here, set this value, come back here, set this value all the time. We can just set this up so we can create one value that'll drive them both. So we'll expose their, not their threshold 2, but their threshold 1. Remember, threshold works where if you do not have inside checked, it will just look at threshold 1 and say, hey, is the value coming in higher than threshold 1? Not if it's lower, just if it's higher. If it's higher, then output true. If it's lower, output false. So what we're going to do then is control threshold 1 and say 100. So if either collision particle A or B has a velocity or a speed greater than 100, and both of those are true, actually if either of them those are true, and they're in that group, so we're going to go ahead and tell and it needs one more thing to evaluate true. Feed you there. Okay, then these VB cell particles will be created. So let's go ahead and play that, or not play it, and let's turn off our debug. Debug will slow you down a little bit. It takes time to pipe the data out and display it, but it is invaluable being able to debug your stuff. Okay, so here comes the second hit. Boom. Yeah, so you see, we'll go ahead and just play it there. The speed is not fast enough, and so the particle, the VB cells are not created. So this is one of the real powers of TP, is setting up these rules and conditions for things that must be true in order for other things to happen. Okay, that's all good, but let's go ahead and actually see what it looks like with our other cool object. Collision environment, not collision environment, but our VB source. For now, let's remove that other one, pick this guy. Oh heck, let's pick both. Collision effects, turn them all into VB source. Now here's a little tidbit. If you can, what you can do is you can actually set up a group here that will force, any born particle or birthed particle into this group operator, which will force it into a specific group, say a VB source. And the only problem is that if you were using object-to-particle tracking, this setup will break it. As soon as you assign it to a different group, object-to-particle tracking, no more. So kind of sad, but true. We do this quite a bit with the group assignment, just because it's an easy way to reduce the amount of clicking we have to do inside this object particle. We don't always want to have to say changes effect all, use your mesh, pick the group. So it's easier just to say, hey, use this group, and then of course we can just pick the instance shape as well. There's actually, we're going to be working on an object particle interface that will kind of help make a lot of this much easier, so watch for that. Okay, so let's turn that off, turn this on, get back here, and we've got our two objects that are all kind of fragmented, if you will, or pre-allocated volume breaker frags. And they are going to hit the ground at a certain speed, and they will break and fragment. You know what, I think our center of mass on this other guy is not quite normal, or is it? Yeah, it's up there. Okay. He was kind of balancing there, if you saw that. Let's actually go ahead and tell our force to be double. Boink. So it looks like we got quite a few more, we had more speed available to us, or affecting the particles, and so this velocity check fired true again, at least for the cube. Let's step through here and look. Bang, that one fires. Or maybe not. Sometimes you can get different results when you scrub versus hitting play. So it's usually best just to go ahead and record your simulation and get the one solid result. Okay, one of the problems though, we can see that one of these pieces on the corner did not activate. So we can either futz with the number of particles being born, or we can just go ahead and tell our volume break, you know what, up your threshold a little bit, and it will kind of affect a little bit further. Boom. Now it kind of takes out all of them there. You can see that. Okay, something else with a volume break is pretty cool is the spreading. So we can tell the spreading, and the spreading size is in a percentage value. So the percentage of the overall original particle shape. So let's say, spread 20%, and time, I believe, is in seconds value, although this one might actually be frame. So we'll go ahead and actually set it to this, and let's actually set it to 100% so we can confirm that spreading time value. Oops, can't quite put that in there, can you? Spreading time 10. 2, 3, 4. It's awfully fast. Okay, but we can see what happens with that spreading time. It goes ahead and, rips through the whole mesh, particle mesh, and breaks it down and activates it. So a spreading time of 30 will actually make it go 3 times longer. And that must be in frame values, but it does not look like it's entirely accurate. It's spreading 100% within about roughly 10 or 15 frames. And our sampling right now is set to per frame. Okay, well, I think that's about it for this video. We're going to go ahead and move on. We're going to go ahead and save this again, just so you have the final result to take a look at.